If you were to stand on the surface of the young Earth 4.5 billion years ago and look up at the sky, you would not recognize the world you were standing on. The sun would rise in the east, as it still does, but it would climb the sky faster than any sunrise you have ever seen. It would race across the dome of heaven in a little over 3 hours. It would set before you had time to grow tired of its light, and then, before the heat of the day could even fully leave the stones beneath your feet, it would rise again. A full day on the young Earth was not 24 hours long. It was 6. 6 hours, from dawn to dusk to dawn. 6 hours for the planet to complete one full rotation on its axis. 6 hours to experience a morning, an afternoon, a night, and the beginning of another morning. A day so short that, by our modern reckoning, you could live 4 of them between breakfast and sleep. This is not a theory. This is not a speculation. This is the quiet, measurable memory of our planet, written in the slow arithmetic of physics and recorded in the microscopic rings of ancient corals. The Earth was once a spinning top, freshly wound, turning so fast on its axis that the day itself was a blur. Tonight, our journey takes us to that impossibly young world. A world where the horizon tilted past you in minutes. A world where the moon hung so close and so huge that it would have filled 1/6 of the sky. A world where the oceans did not simply rise and fall. They heaved and surged and reshaped the coastlines of continents in a single afternoon. We are traveling back to the first day, and we are asking the question that the Earth itself has been slowly, silently answering for 4.5 billion years. Why did our planet slow down? This is not just a story about the length of a day. It is a story about the quiet friction between a world and its moon. It is a story about energy, lost over billions of years, to a silent gravitational conversation happening above our heads every single second. It is the story of how our present, with its 24-hour rhythm of light and darkness, was forged in a tug-of-war that began before the first rain ever fell. Tonight, we will descend through 4.5 billion years of deep time to find the moment the Earth was born spinning. We will watch the young moon, still raw and red, pull at oceans that did not yet have shores. We will walk through the Hadean, the Archean, the Cambrian, and into the age of dinosaurs, measuring the day getting longer, minute by slow minute, across the quiet centuries. And we will ask, at the end, the strange and patient question: when will the spinning finally stop? Because the Earth is still slowing. Every sunrise you witness is, by a tiny, imperceptible fraction, later than the one before it. The day is getting longer. Time itself is being stretched by the silent pull of the moon. But before we get comfortable, if this slow, quiet exploration of deep time is something you genuinely enjoy, I would be grateful if you would like the video and subscribe. And let me know in the comments where you are listening from and what time it is for you. It is always strange and lovely to think about how, somewhere in the world, it is always just after midnight. Now dim the lights. Let the room grow still. Let the soft hum of the night become the sound of a world that is, right now, spinning a little more slowly than it did yesterday. And let us begin. To understand why the Earth spins at all, we have to begin before the Earth existed. We have to begin with a cloud. 4.5 billion years ago, in a quiet arm of a young galaxy, there was a vast, slowly turning cloud of gas and dust. It had no name. It had no borders. It drifted through the cold dark for millions of years, indifferent and patient, composed of the atoms that had once belonged to older, dead stars: hydrogen, helium, traces of carbon and oxygen and silicon, forged in the nuclear furnaces of suns that had already lived and burst and scattered their bodies across the emptiness. This cloud was not at rest. Nothing in the universe is ever truly at rest. It was turning, as all interstellar clouds turn, with a kind of slow, enormous inertia inherited from the rotation of the galaxy itself. It was barely spinning. A single rotation might have taken 1,000,000 years, but it was turning. And then, somewhere deep inside it, the cloud began to collapse. We do not know exactly what triggered the collapse. It may have been the shock wave of a distant supernova, rippling through the void and pressing the cloud's atoms just a little closer together. It may have been the slow inevitability of gravity itself, pulling on a region that had grown slightly denser than the rest. But whatever the cause, a single point within the cloud began to fall inward. And as it fell, it began, like any skater drawing in her arms, to spin faster. This is one of the most elegant and unyielding laws of physics, the conservation of angular momentum. A spinning system that contracts must, by the mathematics of the universe, spin faster. It is why a ballerina can accelerate into a pirouette by pulling her limbs to her center. It is why a dying star collapses into a neutron star that can rotate hundreds of times per second. And it is why a slowly turning cloud of gas, falling under its own gravity, will inherit its rotation and multiply it, turn by turn, into something fast. The cloud that would become our sun, our planet, and everything we know, began to flatten as it spun. The outer regions swung wide, held up by their own momentum. The inner regions fell faster. Over tens of thousands of years, the cloud became a disk. A great, turning wheel of gas and dust, glowing faintly in the infrared, stretching across billions of kilometers, with a dense, hot, hungry center. That center would become our sun. The disk, still spinning, still turning, would become the planets. And every planet born from that disk inherited the same rotation that the cloud had been given by the galaxy itself, multiplied by the physics of collapse, sharpened by every inward fall. When the Earth finally gathered itself out of the dust, it was not still. It could not be still. It was born spinning. It had to spin. The spinning was inherited. The spinning was its birthright. And because the Earth, in those first violent years, was still accreting mass from the disk around it, still being struck, moment by moment, by planetesimals and pebbles and streamers of rock, each collision added, or subtracted, just a little more rotation. The spin was not smooth. The spin was chaotic. But by the time the Earth had become something recognizable, something roughly spherical, something with a molten mantle and a thin, glowing crust, its rotation had settled into a rhythm of 6 hours, a day and a night, together, that fit between the meals of a modern afternoon. This was the first day, not the first day of life, which was still 1 billion years away, not the first day of sunlight filtering through a blue sky, which required an atmosphere the young Earth did not yet have, but the first rotation, the first spin, the first slow announcement, to no one, that the planet had begun to keep time. We tend to think of a day as a permanent thing. The sun rises and sets. It always has. It always will. Our lives are built around this assumption. Our bodies are tuned to it. Our cells, from the simplest bacterium to the most complex neuron, keep an internal clock calibrated to the 24-hour rotation of our world. We call this clock a circadian rhythm, from the Latin circa diem, meaning about a day. It is the oldest rhythm in biology, older than blood, older than bone, older than thought. But that rhythm did not have to be 24 hours. It could have been 6. It once was 6. And if the Earth had formed just slightly differently, if the accretion disk had been slightly less massive, or if the impacts of the early solar system had been slightly gentler or slightly more violent, our day could have been 10 hours, or 4, or 50. The number 24 is not a constant of nature. It is not inscribed anywhere in the laws of the cosmos. It is, like so many of the features of our world, a historical accident, a slow, tidal accident, the result of 4.5 billion years of invisible breaking. Tonight, as you lie still, and the world outside your window turns slowly through its night. I want you to hold that thought. The length of your day is not a given. It is a result. It was forged. It is still being forged. And the forging is so slow, so patient, so quiet, that every generation of humans has lived out their entire life believing that the day they were born into was the same day their ancestors knew and the same day their descendants will inherit. It is not. The day is changing. It has always been changing. And to understand how, we have to go back to the moment the Earth found its first partner in the sky, the Moon. The young Earth was not alone for long. In the chaos of the early solar system, the space around our sun was crowded. Dozens of protoplanets, perhaps hundreds, swung along overlapping orbits, drawing closer, pulling on each other, exchanging material in near misses and outright collisions. The inner solar system was a demolition derby measured in millions of years, and our world was one of the contestants. One of the other contestants was a world we now call Theia. Theia was not small. By the best models, she was roughly the size of Mars, about half the diameter of the young Earth, and around a tenth of its mass. She had her own molten core, her own thickening crust, her own slow rotation. If things had gone just a little differently, she might have become the fifth rocky planet of our solar system. She might have stabilized into a quiet orbit of her own. She might, in some distant alternate timeline, have become a world with oceans, with continents, perhaps even with life. But she shared her orbit with something larger. And in the merciless arithmetic of gravity, two bodies cannot share a single path forever. Over millions of years, Theia and the Earth drifted closer. Their orbits began to resonate. The pull between them grew stronger with every pass. And then, in a morning that no one would ever remember, on a day that had no witnesses, Theia and the Earth collided. This was not a glancing blow. This was not a distant brush. This was a direct, catastrophic impact between two growing worlds, moving at tens of thousands of kilometers per hour, meeting almost head-on. The energy released in that instant is difficult for the mind to hold. It was more than a trillion joules. It was enough to vaporize a significant fraction of both worlds. The crust of the Earth was flung into space. The mantle was torn open. Theia's own body was shattered. Her iron core drove like a hammer into the center of the Earth, merging with our planet's core and adding mass to it. Her lighter mantle, along with a great cloud of vaporized rock from the Earth itself, was thrown outward into orbit. For a time, the Earth was no longer a planet. It was a glowing, molten, half-destroyed thing, surrounded by a ring of rock and dust so hot it shone like a second sun. The surface of our world was not a surface. It was an ocean of liquid magma, thousands of kilometers deep in places, roiling and steaming and radiating heat into space, and the Earth was spinning faster than ever. The impact did not just rearrange matter. It transferred enormous amounts of rotational energy. The angular momentum of Theia's incoming path was partly absorbed by our world. Our planet, already turning, was now hurled into rotation. Some models suggest that in the immediate aftermath of the impact, a full day on Earth might have lasted as little as 2 to 3 hours. A spinning, glowing, wounded globe, rotating so fast that its shape was distorted, bulging at the equator like a drop of water flung from a wheel. It was in this moment that the day was born. The 6-hour day of our story was not the original day. The original day was even shorter. But as the debris in orbit began to gather itself, under its own gravity, into a single body, our moon, the Earth, and its new companion began a long, slow negotiation. Their rotations began to pull on each other. Energy began to flow between them. The moon, tugged outward by tidal forces, began to drift away from our world, just a little, every year, and the Earth, in return, began to slow. By the time the moon had fully formed, perhaps a few thousand years after the impact, it hung close to our world, astonishingly close. Current estimates place the newborn moon at a distance of only about 22,000 to 30,000 kilometers from the Earth's center. For comparison, the moon tonight hangs at an average distance of 384,000 kilometers. The moon that rose over the molten Earth was more than 10 times closer than the moon you might see if you stepped outside this evening. At that distance, the moon would have filled a large section of the sky, not a small pale disk as we see it now, but a great, looming presence. If you could have stood on a cooling crust of that early Earth and survived the radiation and the heat and the meteor bombardment, you would have looked up and seen a world beside you, a world with detail, a world with shadows and craters and streams of still glowing lava flowing down its newborn mountains, a world that, because of the tides it raised on our still molten surface, was already beginning to slow our spin. This is the beginning of the story of our 6-hour day, because by the time the Earth's surface had cooled enough to hold onto water, by the time the first oceans had rained out of the steam atmosphere and begun to collect in the low basins of our young crust, the Earth's rotation had already slowed considerably from its post-impact extreme. The 2-hour day was gone. The 3-hour day was gone. The Earth was turning once every 4 hours, then 5, then 6. The 6-hour day is, in a sense, the first stable day, the first day you could measure, the first day that had a morning and an evening that lasted long enough for a rock to warm and cool and warm again. It is the day that held the Earth for most of its first billion years, a day that watched the oceans form, a day that watched the first atmosphere settle into place, a day that, very slowly, watched the first molecules of life begin to organize themselves in the tide pools of a world still half wrapped in fire. We tend to imagine the early Earth as silent, as dark, as empty. And in a sense, it was. There were no birds, there were no crickets, there were no human voices, there was no one to hear. But there was sound. There was always sound. The sound of a 6-hour day was the sound of a world in violent motion. The sound of tides crashing against shores made of fresh basalt. The sound of volcanoes, more numerous and more active than anything alive on Earth today, venting steam and ash into a thick, orange atmosphere. The sound of lightning, constant and unceasing, flickering across a sky that had never known a human eye. The sound of meteorites, still striking the surface every few minutes, cracking the crust, adding heat, adding water, adding complexity. And above all of it, the sound of the spin, the ceaseless, silent turning of a planet on its axis. The quiet gravitational conversation between a world and its moon, a conversation conducted in the language of oceans and stone. 6 hours for the sun to cross the sky, 6 hours for the moon to race along its orbit, 6 hours for the young Earth to turn once beneath the stars. And somewhere in that hot, bright, turning world, in the chemistry of the first oceans, something was beginning. Something that would, billions of years later, lift its head from the water, look at the moon, and begin to wonder, but that is still a very long way away. For now, the Earth simply spins. It spins fast because it was born fast. It spins hot because it is still cooling. It spins loud because it has no soil yet to soften its surface, no forests yet to muffle its winds, no atmosphere yet thick enough to calm its lightning. And above it all, the moon orbits and pulls and whispers a slow, patient instruction to the planet below. Slow down, slow down, slow down. The Earth listens. It has no choice. It will listen for 4.5 billion years. There is a photograph taken by one of the Apollo astronauts of the Earth rising over the surface of the moon. In it, our world is a small, blue, fragile thing, half-shadowed, hanging in the black of space. It is one of the most famous images ever captured, and it is, in a strange way, backward. Because for most of Earth's history, it was the moon that loomed, not the Earth. The moon was closer. The moon was larger. The moon dominated the sky. If you could stand on the Earth 4.5 billion years ago and look up, you would not see the small, distant companion we see tonight. You would see a second world. Not a pale disk hanging behind a thin veil of cloud, but a full, globe-sized body taking up a measurable fraction of the sky. Imagine looking at the moon tonight. Now, imagine it a dozen times wider, not twice as wide, not 3 times. Imagine it so large that it curves visibly against the black of space. Imagine seeing the Terminator, the line between its lit and unlit halves, sweeping across its face in real time, as the moon rotated and as the Earth beneath you turned. This was the moon of the 6-hour day. This was the moon of the first oceans. At 22,000 kilometers distance, the moon would have occupied roughly 12 to 15 degrees of sky. For comparison, your clenched fist, held at arm's length, covers about 10 degrees. So imagine a moon roughly the width of your fist and a little more. A moon that, even in daylight, was impossible to ignore. A moon that cast a ghost shadow through the clouds. A moon whose light, when it rose at night over the molten plains, was enough to read by, if there had been anyone to read. The moon, at that distance, was also moving differently than it does today. Tonight, the moon takes roughly 27 days to complete one orbit around the Earth. It rises, crosses the sky, and sets, and it appears once each night in roughly the same place in our sky, shifting only slightly from one night to the next. It is a slow, stately companion, a kind of patient, circling witness. But when the moon hung at 22,000 kilometers, when the Earth rotated every 6 hours, the moon itself orbited the Earth in a little over 8 hours. It completed one full loop around our world in about the time you sleep at night. This means that on the early Earth, the moon did not stay put. It moved. It moved visibly. It moved quickly. It climbed across the sky in a rush, setting faster than any star we know. And because the Earth was also spinning so quickly, the moon's motion relative to the horizon was a strange, layered thing. Sometimes it appeared to race with the sun. Sometimes it appeared to lag behind. Depending on the day, the moon could rise twice in a single Earth day, crossing the sky faster than the shadows of the rocks could lengthen. It was not a predictable object. It was not a gentle one. And it was not safe. At 22,000 kilometers, the tidal force between the Earth and the moon was hundreds of times stronger than it is tonight. Tides are not a matter of the moon's absolute pull. They are a matter of the difference in pull between one side of the Earth and the other. The closer the moon, the greater that difference. And the greater the difference, the more the oceans, and even the solid crust, are stretched and deformed. On the Earth of the 6-hour day, the tides were not the modest 2-meter rise and fall of a modern Pacific beach. The tides were mountains of water, hundreds of meters high. In some models, the first tides of the newborn ocean may have reached a kilometer in amplitude, sloshing across a hemisphere in a matter of hours, rising and falling with the rapid orbit of a moon that hung overhead like a second world. These were not tides as we know them. These were tidal continents. Each rotation of the Earth carried the tidal bulge across the face of the planet multiple times. The oceans were in a state of constant, violent motion, churning, mixing, eroding the young crust, carrying dissolved minerals from continent to deep basin and back again. And the tides did not only move water, they moved the Earth itself. At that distance, the moon's gravitational pull was strong enough to flex the solid rock of the Earth's crust by meters. The entire planet, as it rotated, breathed in and out under the moon's pull, like a lung expanding and contracting. This flexing generated friction. The friction generated heat. The heat drove volcanic activity. Some scientists have proposed that the extreme tidal heating of the early Earth may have helped keep the planet's interior molten for longer than it otherwise would have. The moon was not only a celestial companion, it was a furnace, a gravitational furnace, keeping the young Earth warm from the inside. But there is another, stranger consequence of the moon's closeness. The moon was, in every visible way, a second sun. When the sun set on the Earth of the 6-hour day, the darkness that followed was not absolute. If the moon was up, it lit the world with a light that would have been many times brighter than the full moon we know. The reflected sunlight from a disk that large, at that distance, would have cast sharp shadows. The night would have had color. The night would have had depth. The night would have been a kind of silver daylight, strange and soft, lasting for the 2 or 3 hours that the moon ruled the sky before it dipped below the horizon and the true dark, thin and brief, finally arrived. It is impossible not to wonder what this would have looked like, and it is one of the quiet tragedies of deep time that no one was there to see it. There were no eyes. There were no minds. The Earth performed its most spectacular sky pageant alone, for billions of nights, for no audience at all, while the moon raced overhead and the oceans heaved and the volcanoes answered from below. This is what we mean, on this channel, when we speak of the silence of the Earth. Not that the Earth was quiet. It was, in truth, one of the loudest eras our planet would ever know. But it was silent in the sense that mattered most. It was silent in that there was no one to hear, no one to remember, no one to lie awake, as you may be lying awake now, and wonder at the strangeness of a world that had a moon for a ceiling and a day that ended before the rocks had time to cool. The moon was there, the tides were there, the light was there, but the witness was not. And it would not arrive for a very, very long time. Tonight, as the moon outside your window hangs in its distant, modern orbit, tiny and pale and predictable, I want you to hold this image with you. The moon you see now is not the moon that was, the moon that was filled the sky, the moon that was raced across it, the moon that was raised oceans into the air and held them there. And the moon that was is, at this very moment, still moving away from us. Every year, the moon retreats by about 3.8 centimeters. Slow, patient, relentless. It has been moving away for 4.5 billion years. And every centimeter of its retreat is paid for, silently, by a tiny lengthening of our day. The moon steals our rotation, and the Earth, quietly, lets it. Consider what this exchange actually is. When the moon pulls on the ocean, it raises a bulge of water beneath itself. But the Earth, spinning faster than the moon orbits, drags that bulge ahead, just slightly, of the moon's position overhead. The bulge sits a little east of where the moon actually is. And because the bulge has mass, it exerts its own tiny gravitational pull. It tugs the moon forward along its orbit, giving the moon a small, constant boost of energy. That energy has to come from somewhere. It comes from the Earth's rotation. The moon, pulled forward, climbs into a higher orbit. The Earth, slowed by the drag of its own tidal bulge, turns a tiny fraction more slowly each day. This exchange is so small, on any human time scale, that it is effectively invisible. Across a single human lifetime, the day lengthens by less than 1,000th of a second. Across the 2,000 years since the time of the Roman Empire, the day has lengthened by roughly 1/20th of a second. You could not feel it. You could not measure it without extremely precise instruments. But across billions of years, this quiet, ceaseless theft adds up. It adds up to hours. It adds up to days. It adds up to the entire difference between the world we live in and the world the Earth was born into. The moon has been taking our rotation, atom by atom, tide by tide, for 4.5 billion years. And the Earth, turning now at a leisurely 24 hours per spin, has been paying that debt faithfully, without complaint, without rest. Every sunrise is a small surrender. Every sunset is a small goodbye. The moon drifts a little further. The day grows a little longer. The night stretches by a fraction of a second. And nothing, in the laws of physics as we currently understand them, We'll stop this process until the Earth and the Moon are locked, face to face, turning together in a shared rhythm they can no longer alter. But that is the end of the story, and we are still at the beginning. We are still, in our imagination, on the shore of a molten world, looking up at a moon that fills the sky, listening to the sound of a tidal wave that comes 4 times a day and shakes the ground beneath our feet. The moon was close, the Earth was young, and the day was only 6 hours long. The period of Earth's history in which the 6-hour day was born has a name. Geologists call it the Hadean, after Hades, the Greek underworld. The name is not accidental. It is meant to convey a place of fire, of heat, of shadow, of things not yet formed. It is a name for an era before names, an era before fossils, an era before the rocks we can hold in our hands today would have existed in any recognizable form. The Hadean stretched from the formation of the Earth, roughly 4.54 billion years ago, to about 4 billion years ago, 540 million years, longer than the entire history of complex animal life on this planet, longer than the entire story of fish, insects, plants, forests, reptiles, mammals, humans, combined many times over. And yet, we have almost no direct record of it. The oldest surviving rocks on Earth are about 4 billion years old, and they are small, rare, and scattered. The oldest mineral grains, tiny crystals of zircon preserved inside younger rocks, reach back to about 4.4 billion years. These zircons are the Hadean's only witnesses. Small, hard, patient, almost indestructible. They carry in their chemistry the memory of the world they were born in, and what they tell us is strange. They tell us that the Earth of the Hadean was not quite as hellish as the name suggests. Yes, there was volcanism. Yes, there was meteor bombardment. Yes, there were long periods in which the surface was molten, or nearly so. But the zircons also tell us that, even in the earliest Hadean, there was liquid water. There were oceans, or something like them. The Earth cooled faster than we once thought. The crust formed, broke, reformed, and broke again. But in between these breakings, there were intervals of relative quiet. Intervals in which the Earth was not a glowing ball of lava, but a dark, ocean-covered world with a thick, orange atmosphere, a close and looming moon, and tides that moved like tectonic events every 6 hours. In those intervals, the Earth was not peaceful, but it was recognizable. It was a planet. It had weather. It had rain, salt, wind. It had sunrise and sunset, over and over, 4 times every day. Imagine, if you can, a shore on such an Earth. The sand would not be like modern sand. It would be coarse, black, glassy, composed of fragments of fresh basalt and olivine and still cooling lava. The water would not be blue. The atmosphere had almost no free oxygen, and the sky, heavy with carbon dioxide and methane and sulfur compounds, would filter the light into strange colors. The sea would have been orange or red, or the color of weak tea, depending on the chemistry of the dissolved iron and the hour of the day. The horizon would have been closer than you expect, because the air was denser, heavier, compressed by the gravity of a world that held on to everything. And above this shore, the sky would have been moving, fast. The sun would rise in an unfamiliar place, because the Earth's axis in those early days was not yet stable. It would climb steeply, heating the young ocean, drawing up a violent evaporation. The clouds would form and break, and form again within minutes. The wind would race, constant and hot, because the rapid rotation of the Earth generated a powerful Coriolis effect, driving winds faster and more turbulent than anything modern meteorology records. There were no tropical calms, there were no gentle breezes, there were only gales, and gales, and gales. Then, after 3 hours of blazing, turning daylight, the sun would drop toward the horizon, The sky would darken not to black but to deep, glowing red, and the moon would rise, enormous, close, silver against the fading sun. The moon would light the second half of the day. The rocks would cool, but only a little. The ocean would settle, but only for minutes, before the incoming tide, the real tide, the great mountain of water that the moon was pulling across the face of the world, arrived. And when the tidal wave came, it came with the sound of 1,000 thunderstorms. This is something worth pausing on. The tidal wave of the 6-hour Earth was not a wave in the ordinary sense. It was a bulge in the ocean, raised up by the moon, that swept around the planet in lockstep with the moon's motion through the sky. Because the moon orbited so fast, and because the tidal force was so strong, this bulge was steep, tall, and fast-moving. In open ocean, it would have been perhaps hundreds of meters tall. Enormous by modern standards, but manageable. Because in open water, the bulge was spread over vast areas. But when the tidal bulge reached shallow water, when it crashed into the continents and the basin margins, it rose. The same physics that turns a small ocean swell into a 20-meter wave on a reef turned the Hadean tide into a wall of water that could be a kilometer high. It would surge inland across hundreds of kilometers, scouring everything in its path, depositing a fresh layer of black sand and mineral fragments, and then, 4 hours later, would retreat with equal violence. This happened every 6 hours, forever, for millions of years. No continent, as we understand it, could stabilize under such tides. The land was constantly being remade. The oceans were constantly mixing. The minerals dissolved in the Hadean seas were being redistributed every few hours across the entire planet. And in that constant stirring, in that endless tidal mixing, something was happening that would matter more than any of the rest of it. Chemistry was beginning. The Hadean ocean was rich in dissolved compounds. Carbon, in the form of methane and carbon dioxide and simple organic molecules, was everywhere. Nitrogen was plentiful. Phosphorus, washed out of the lava, was present in the tide pools. Hydrogen, escaping from volcanic vents, drifted through the water and the air. And in the shallow margins of the Hadean Sea, where the tide came and went every few hours, the chemistry of the planet was being experimented upon on a planetary scale, again and again and again. The short day of the early Earth may have mattered for life in ways we are only beginning to understand. A 6-hour day means a rapid cycle of heating and cooling. It means that a tide pool, warmed by the sun for 3 hours, was then plunged into shadow and chilled for 3 more, before being flooded and scoured and flooded again. Each cycle concentrated certain molecules and diluted others. Each cycle created conditions for chemical reactions that could only happen on the boundary between wet and dry. Each cycle, some scientists now argue, may have been a tiny planetary factory, running the same experiments trillions of times at once, across millions of shores, for hundreds of millions of years. The day did not need to be long for chemistry to happen. The day needed to be rhythmic, and the rhythm of the Hadean was the rhythm of 6 hours, 4 cycles a day. 4 cycles a day, every day, for 500 million years. Roughly 730 billion cycles of tidal wetting and drying on every shore of the young Earth, before the first truly stable continents had even formed. In that unfathomable number of cycles, something happened. We do not know, and may never know, exactly what it was, but somewhere, on some shore, in some particular combination of minerals and organic molecules and repeated tides, the chemistry crossed a threshold. Simple molecules began to replicate. Not in the full, elegant, DNA-based way that modern life replicates. Something simpler, something cruder, something that would be unrecognizable to a modern biologist. But something that, once started, could not be stopped. Something that copied itself. Something that persisted. Life began on a planet whose day was shorter than the shift of a modern hospital nurse. And the Earth kept turning. 6 hours, 6 hours, 6 hours. It is worth sitting for a moment with the pure oddness of this. We tend to think of life as inseparable from the world we know, from grass, from trees, from the slow green rhythm of the seasons. But life, in its first forms, knew none of those things. It knew only tides, fast, furious tides, coming and going every few hours. It knew heat, intense and brief. It knew darkness, intense and brief. It knew the glare of a sun that crossed the sky faster than the shadow of a storm front. It knew the silver light of a moon that filled a sixth of the heavens. Those first molecules of life were tuned to a 6-hour day. Their chemistry, their cycles, their replication may have been calibrated to the tempo of a world that no longer exists. Some researchers have suggested that the deep rhythms of our own cells, the oldest biological rhythms we can trace, carry faint memories of that ancient tempo, a hidden pulse buried inside the genomes of bacteria that still beats to a drum no longer played. Tonight, as you lie still, and the slow, modern rhythm of your own breathing rises and falls, try to hold that thought in the softness of your sleep. The life inside you, the cells, the proteins, the molecules, descends in an unbroken line from ancestors whose only sky was the Hadean sky, whose only clock was the 6-hour spin, whose only horizon was the orange-red foam of a tidal wave they did not fear because they could not fear anything. They only copied and persisted and copied again. This is where you come from. A short day, a close moon, a fast sky, a strange, patient chemistry, doing its work on the shores of a world that had nothing to lose. By the end of the Hadean, the Earth was no longer quite the molten nightmare it had been at its birth. The bombardment from the early solar system was tapering off. The crust had settled. The oceans had become something permanent, or at least something that returned, after every catastrophe, to a recognizable form. The atmosphere had thinned and stabilized, though it was still nothing like the air you breathe tonight. The moon had receded, slightly. The day had lengthened, slightly, but only slightly. By 4 billion years ago, at the boundary between the Hadean and what geologists call the Archean, the Earth's day had grown from 6 hours to perhaps 8 or 9. A measurable change, but a small one. The planet was still a fast-spinning young world. The tides were still enormous. The moon, though further away than it had been, was still close enough to dominate the sky. And life, tiny and anonymous and unrecorded, had taken hold. Microbial mats, perhaps. Simple colonies of organisms that could photosynthesize, or chemosynthesize, or ferment, or simply persist. The first great experiment in biology was underway, and its first subjects knew nothing of the world except heat, salt, and the relentless beat of a 6-hour tide. The Hadean is the only era in Earth's history that has no fossils. Not a single preserved organism, not a single shell, bone, leaf, or footprint. It is a time before memory. It is the true silence before the long song of life. And yet, without the Hadean, without the 6-hour day, without the fast tides and the short nights and the rapid cycles of wet and dry, none of what followed would have followed. The day did not just measure time. The day made time meaningful. The day gave the Earth its first rhythm, and from that rhythm, eventually, came everything else. There is a strange intimacy to mornings. You have had thousands of them. You will have thousands more. Every morning, the Earth you stand on turns its face toward the sun, and the sun, 93 million miles away, unchanged and indifferent, lays its light upon you again. The sky brightens. The world resolves out of dark shapes into known shapes. A room, a window, a street, a tree. You recognize it all. You have always recognized it. It is your first and oldest story. this return of the light. But mornings as you know them are not ancient. Mornings as you know them did not exist for most of Earth's history. The morning of the 6-hour day was a different thing. It was fast, it was brief, it was strange. Picture a shore on the late Hadean Earth, perhaps 3.5 billion years ago. The planet has cooled somewhat. The oceans are stable, more or less. The atmosphere has settled into a thick, warm, humid blanket of nitrogen, carbon dioxide, water vapor, and trace methane. There is still no free oxygen to speak of. The sky is not yet blue. It is a hazy, orange-brown dome, smeared with low clouds that form and dissolve in minutes. The land is almost entirely made of bare, dark volcanic rock, with a thin film of microbial life clinging to its wetter surfaces. The night has been short, less than 3 hours. The moon has raced across the sky, set, and now, somewhere beneath the eastern horizon, the sun is returning. Dawn begins differently on a fast-spinning Earth. On our modern planet, dawn is a slow, generous thing. It lasts for a long half-hour or more, depending on your latitude. The sky brightens gradually. The horizon glows. The colors shift through soft grays and pinks and blues before the sun finally breaks over the edge of the world. You can watch the whole process. You can think while it happens. You can drink a coffee. On the 6-hour Earth, dawn was faster. Because the planet turned 4 times in 24 hours, the sun swept across the horizon at 4 times the angular speed we know. The sky did not have time to settle into one color before it became another. The transition from full night to full day lasted, by some estimates, less than 10 minutes. You would barely see the first gray of the eastern sky before the horizon would flame with red, and red would flame into amber, and amber into the strange orange-pink of a Hadean morning. And then, almost before you could turn toward it, the sun itself would breach the horizon, a white fury, a newborn star in a hurry. The warmth that followed was different too. On the modern Earth, a sunrise warms the air by a few degrees in the first hour. On the 6-hour Earth, the sun climbed the sky so quickly that the temperature of the air could rise by 10, 15, 20 degrees in the same span. The ground, already radiating heat from the night, would begin to smoke. Water vapor would rise in shimmering columns off the wet rocks. Steam would fog the low places. And above it all, the sky, turning with the planet, would be so full of motion that it seemed alive. 3 hours of this. Only 3 hours of day. 3 hours in which the sun climbed, peaked, and began to fall again. The shortest, fiercest afternoon you can imagine, bracketed by dawns and dusks that came and went in minutes. There is something almost musical about this rhythm when you think about it for long enough. Beat, 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 beat. 4 times a day, the sun rose. 4 times a day, the sun set. 4 times a day, the tide came and went. 4 times a day, the moon appeared or disappeared somewhere in the sky. The Earth was not a patient world, as it is tonight. It was an urgent world. Everything happened quickly. Every rhythm was compressed. Every cycle was brief. And in this rapid, drumming tempo, the first truly living things began to take notice. Some of the earliest life on Earth, the cyanobacteria, evolved a very particular trick. They learned to split water molecules using the energy of sunlight. They learned to photosynthesize, and they learned, without knowing anything, to track the sun. Modern cyanobacteria still carry what are called circadian genes, genes that run a molecular clock synchronized to the daily cycle of light and dark. These genes allow the organism to anticipate sunrise, to prepare its photosynthetic machinery before the light arrives, to shut down other processes when the sun goes down. It is one of the oldest known biological clocks. It is older than animals. It is older than plants. It is older than almost anything we recognize as life, And when scientists study the molecular architecture of these ancient clocks, they find something curious. The machinery is not perfectly tuned to a 24-hour cycle. It is flexible. It can be reset, and in some species, it seems to carry echoes of cycles shorter than 24 hours, much shorter. Some researchers have speculated, though the evidence is still thin and the debate is ongoing, that the circadian clocks of the earliest photosynthetic organisms may have been tuned to a 6-hour or 10-hour day. That as the Earth's rotation slowed, the clocks of life slowed with it, gradually, over hundreds of millions of years. That the rhythm of our own cells, right now, as you fall towards sleep, is the slow descendant of a rhythm that once beat 4 times faster than it does today. If that is true, it is an astonishing thought. The tempo of your body is the tempo of the Earth. The tempo of the Earth was once the tempo of a 6-hour day. And somewhere, impossibly deep inside you, there is still a memory of mornings that came and went in minutes, under a moon that filled the sky, beside tides that could crush whole shorelines every 4 hours. The first morning was not a human morning, but it may have been the morning that taught life what a morning was. From that first lesson, everything else followed. Light and dark became the 2 great teachers. Every organism that ever evolved eyes evolved them because of the light. Every organism that ever evolved sleep evolved it because of the dark. Every organism that ever evolved memory, for that matter, evolved it in part to remember the difference between day and night. The daily rhythm became the frame on which biology built itself. And the frame was set, originally, by a spinning Earth that turned 4 times faster than it does now. It is strange to think that the reason you feel tired at the end of your day is because 3.5 billion years ago, a cyanobacterium in a tide pool on the Haitian shore began to anticipate the sunset. But it is true. Everything we call life is descended from that first, simple, patient anticipation. And every night you have ever fallen asleep is, in some sense, a return to a habit begun before there were bones, before there were brains, before there was anything on this planet that we would today recognize as alive. A habit begun under a fast sun, a habit kept patiently as the day grew longer. A habit that still holds you tonight as the sun sets on your side of the world and the Earth, turning slowly now, gives you the long, long night that the Haitian never knew. By about 3 billion years ago, the Earth had slowed further still. The day was perhaps 15 hours long. The moon had retreated to around half its modern distance. The tides were still large, but no longer planetary catastrophes. The crust had thickened. The first true continents, small, scattered, primitive, were beginning to assemble themselves. The sky was still orange-brown, but a new chemistry was beginning to rise into it. Oxygen, produced, slowly, by the patient work of countless trillions of cyanobacteria, splitting water and releasing, as a waste product, the gas that would one day make animals possible. The first oxygen did not enter a blue sky. It entered a sky that was still the color of rust, and at first, it did not accumulate in the air. It was absorbed by the dissolved iron in the oceans, oxidizing that iron and precipitating it out of the water as the great banded iron formations we still mine today. For hundreds of millions of years, the cyanobacteria breathed out oxygen, and the oceans drank it, and the banded iron settled silently to the seafloor. Only when the oceans could hold no more, only when the iron had all been rusted, did oxygen finally begin to leak into the air. This is called the Great Oxygenation Event. And when it happened, the world changed. The sky turned blue. The sea turned blue. And the day, still lengthening, still slowing, had a new color to illuminate. A blue sky is not a trivial thing. It is the signature of a world with a particular atmospheric chemistry, a particular oxygen concentration, a particular scattering of sunlight through a thin veil of air. Most planets do not have blue skies. Mars has a butterscotch sky. Venus, beneath its clouds, has a dim, red-orange sky. Titan has an orange sky. The Earth's blue, that calm, familiar, endless blue, is a very particular accident of chemistry and history, and it arrived, in its modern form, only about 2 billion years ago, which means, for most of Earth's history, including the entire 6-hour era, the sky was not the sky you know. Hold that thought for a moment. You have lived your entire life under a blue sky. You have assumed, without thinking, that blue is the natural color of day. But blue is young. Blue is new. Blue is one of the more recent features of our planet, geologically speaking. For the first 2 billion years, the Earth lived its life under an orange ceiling, beneath a close moon, turning once every 6 hours, 8 hours, 10 hours, and finally 12, 13, 15. And throughout all that time, beneath all those different colored skies, life continued. Microbial life, at first, slow and unambitious. Later, slightly more complex life. Much later still, the first hints of what would become animals. The day lengthened, the moon retreated, the tides calmed, the atmosphere evolved, but life persisted. The short day of the young Earth was long enough for life to begin. The lengthening day of the Middle Earth was long enough for life to diversify. And somewhere, in the slow, patient arithmetic of tidal friction, in the long, quiet breaking of a spinning planet by a distant moon, a rhythm was being prepared that would one day cradle eyes, and nerves, and memory, and the kind of mind that could lie still at night and wonder about its own origins. That rhythm is the rhythm you feel now, 24 hours. A day long enough for a morning, an afternoon, an evening, and a night. A day long enough to rest, a day long enough to dream. It was not always this way. It took 4.5 billion years of spinning, slowing, drifting, friction, tide, and silence to shape the day into the one you are falling asleep inside of now. And it is still not finished. The Earth is still slowing. The day is still growing. The rhythm you feel tonight is not the rhythm your descendants, 100 million years from now, will feel. Theirs will be slower, longer, stranger, but that is a later chapter. For now, let the first light of that ancient morning fade. Let the fast sun sink behind a horizon it has just barely risen above. Let the tide come in, one more time, to a shore that has no name. And let the moon, impossibly close and impossibly bright, rise silver over the long, orange sea of a world that is only beginning to learn what a day can become. The Earth is turning. The Earth has always been turning. And tonight, it will keep turning, patiently, beneath you while you sleep. There is a word that geologists use for the next 2.5 billion years of Earth's history. Archean, from the Greek arche, meaning beginning or origin. It is the age of origins, the age when the basic rules of our living world were written. The Archean began roughly 4 billion years ago and lasted until about 2.5 billion years ago. For a full third of the entire history of our planet, the Earth was an Archean world. And yet, if you stood on it, you would still not quite recognize it. The moon had retreated further. By the start of the Archean, it hung perhaps 200,000 kilometers away, half the distance we see tonight. The day had lengthened. A single Earth rotation in the early Archean took perhaps 9 or 10 hours. Still fast, still strange, but no longer impossibly short. The sun, in the early Archean, was faint. This is one of the quiet puzzles of our planet's history. By the laws of stellar evolution, a young sun gives less light than a mature one. Our sun at the start of the Archean was perhaps 25 to 30% less luminous than it is today. If the Earth had its modern atmosphere, with its modern mix of gases, The planet should have been frozen solid during the Archean. The oceans should have been ice. The surface should have been white. And yet, the rocks tell us that the Archean Earth had liquid oceans. It had weather. It had a warm climate, by the evidence, warmer in many places than our own. This puzzle is called the faint young sun paradox, and it is a paradox in the true sense of the word. It is a contradiction between what the physics of stars tells us and what the rocks of the earth tell us. Both cannot be right, and so both cannot be wrong. Something in our model of the Archean must be missing. The current best answers involve the atmosphere. The Archean air was heavy with greenhouse gases, carbon dioxide in concentrations we would find poisonous, methane, produced by the first life forms, trapping infrared radiation against the surface, perhaps nitrogen at a higher partial pressure than today. Together, these gases may have kept the Archean Earth warm enough for liquid water, despite a dimmer sun. But there is another possible contributor: the spin. A rapidly rotating planet distributes heat differently than a slowly rotating one. The Coriolis effect, which drives atmospheric circulation, is stronger. The tropical belt of warm air is narrower. The polar regions are, in some models, comparatively warmer, because heat is more efficiently pushed poleward by the patterns of atmospheric flow. A fast-spinning Earth, under a faint sun, may have been able to hold on to its warmth in ways that a slower spinning Earth could not. Everything on our planet is connected. The length of the day shapes the motion of the air. The motion of the air shapes the climate. The climate shapes the ocean. The ocean shapes the chemistry. The chemistry shapes life. And life, eventually, reshapes all of it. In the early Archean, life was still very simple. It was microbial. It was single-celled. It lived in the sea. It clung to shorelines, to hydrothermal vents, to the slick mineral films of shallow bays. It built, slowly, the first stromatolites, domes and mounds and sheets of microbial communities, trapping sediment, layer after layer, building stone out of patience. If you had walked along the shore of an Archean sea, you would have seen them. Mounds of layered rock, the size of loaves of bread, or wheels of cheese, or small boulders. Living mats on their outer surfaces, fossilizing slowly in their interiors, gently wet by the tide, gently warm in the sun, gently covered every 10 or 11 hours by the incoming sea. These were the first structures built by life on Earth. Not nests, not burrows, not reefs, but domes, laid down by the slow accumulation of microscopic cooperation in the steady rhythm of a day that was still not quite as long as ours. The moon at the start of the Archean was still large in the sky, not as large as in the Hadean, but larger than we know, perhaps 2 or 3 times the apparent size of the moon tonight. It would still have cast a light strong enough to see by. It would still have moved visibly across the sky, orbiting every 18 or 20 hours. And the tide it raised, still substantial, still swept across the shallow seas in great fast pulses, maintaining the rhythmic wetting and drying that life had come to depend upon. Over the next billion years of the Archean, the moon continued its slow outward drift. The day continued its slow lengthening. 10 hours became 11. 11 became 12. By 2.5 billion years ago, the Earth was rotating in roughly 18 hours, a day that, by our modern standards, was finally starting to feel a little more familiar. A full sunrise to sunset might have lasted 9 hours. A full night, another 9. A creature, if there had been anything complex enough to be called a creature, could have rested for nearly as long as we rest, and then risen into a morning not unlike the mornings we know. But in the Archean, there were still no creatures. There were still only microbes. They carpeted the shallow seas. They reddened the stones of the ocean floor with the iron they processed. They built their patient stromatolites. They did something else, too, something that would, eventually, almost end all life. They began to make oxygen. Somewhere in the middle of the Archean, a new kind of photosynthesis evolved. Earlier photosynthesis had used simpler molecules, like hydrogen sulfide, as its chemical partner. The waste product was often sulfur, harmless, containable. But the new photosynthesis, practiced by ancestors of modern cyanobacteria, used water. It split water molecules using sunlight, took the hydrogen, and released, as a waste product, oxygen. Oxygen, the gas we breathe, the gas that keeps us alive, the gas without which the modern biosphere could not exist. It was, to the Archean world, poison. Oxygen is a violently reactive molecule. It corrodes metal. It burns organic matter. It tears apart the delicate biochemistry of cells that have not evolved to handle it. For most of the Archean, oxygen released by cyanobacteria was absorbed by the environment. It reacted with dissolved iron in the sea, forming vast beds of iron oxide that we still mine today. It reacted with minerals on the sea floor. It was locked into the rocks as fast as it could be produced. But the cyanobacteria did not stop. They kept producing. And eventually, around 2.5 billion years ago, the iron sinks were full. The sea could absorb no more. The oxygen began to accumulate in the water, and then, for the first time in the history of our planet, to escape into the atmosphere. This moment has a name. Geologists call it the Great Oxidation Event. It is one of the most consequential transitions in the history of Earth, and perhaps in the history of the universe, as far as we can see. The air changed. For the first time, free oxygen, the same oxygen that keeps you alive tonight, began to fill the sky. Within a relatively short period of geological time, perhaps 100 million years, the oxygen concentration in the atmosphere rose from nearly nothing to a small but significant fraction. The sky, once orange and hazy under its blanket of methane, began to clear. The first blue began to appear overhead, and across the Earth, life paid a terrible price. Most of the organisms that had dominated the Archean could not tolerate oxygen. They lived in anoxic water, in the absence of this new gas, and they could not adapt to its rise. As oxygen spread, they retreated. They sank into the muds. They crowded into hydrothermal vents and deep-sea basins where the new atmosphere could not reach them. Many lineages simply died. We do not know how many. The fossil record of microbial life is too faint for us to count. But it is almost certain that the Great Oxidation Event caused one of the largest mass extinctions in the history of our planet, invisible because its victims were microscopic and left no bones behind. And all of this happened on a planet whose day was still only 18 hours long. A planet whose moon, in the sky, was still noticeably larger than our own. A planet whose tides still moved faster, whose climate was still stranger, whose seas were still stirred by rhythms that modern Earth has long forgotten. The first real morning on Earth, in the sense of a morning with a blue sky, with breathable air, with the possibility of complex life, was an Archean morning. It came slowly. It came partially. It came at a terrible cost to the organisms that had built the world before it. But it came. And when it came to a planet whose day was still not quite ours. A planet still turning faster than we do. A planet still listening to the moon. A planet still building, slowly, patiently, the conditions that would one day, billions of years later, make it possible for you to lie still in the dark and listen to this story. Tonight, as you breathe, every breath you take pulls in oxygen that is, in part, the inheritance of those Archean cyanobacteria. The atmosphere you inhabit was assembled by life. Your lungs are filled by the exhalations of an ocean that learned, a long time ago, to split water with sunlight, and the whole process took place on a world that, at the time, was still spinning fast, still turning every 18 hours, still, in a sense, finding its rhythm. The day was lengthening, the moon was retreating, life was changing, and the earth, in its patient, silent way, was settling into a slower pulse. There is a kind of water that does not exist anymore. On the modern earth, the tide is a familiar, almost domesticated thing. It rises, it falls, it etches a dark line of seaweed and shell onto the rocks of our coasts, and then it retreats, leaving behind pools that children peer into, looking for crabs. A tide of 2 meters feels significant. A tide of 10 meters is famous. The tides of the Bay of Fundy in Canada, where the water can rise and fall by 15 meters, are a tourist attraction, one of the last places on our planet where the ocean still moves with anything like its old voice. But the tides of the young Earth were nothing like the tides we know. When the moon was close, the tidal force was a planetary event. It was not the quiet rhythmic whisper of a sea that remembers to check in twice a day. It was a surge that redrew the geography of every coastline, every few hours, for hundreds of millions of years. It carved, it drowned, it mixed. It carried the chemistry of the deep ocean into the shallowest bays, and then dragged the sediment of the shallow bays out into the deep. It never rested. It never paused. It moved with the relentless patience of the moon itself. Let us try to picture it. Let us stand, in our imagination, on a continental shelf near the end of the Hadean, perhaps 3.5 billion years ago, when the moon hung perhaps 80 to 100,000 kilometers away, and the Earth turned in about 8 hours. The land beneath our feet is low, very low. The continents in this era are not yet the great thick slabs of modern geology. They are thinner, more fragmented, and they sit only a little above the level of the sea. Much of what will one day be dry land is still underwater, or only barely emergent, a brown smear of basalt and early granite peeking above a warm, salty ocean. The sun is overhead, shining through a thin, pale atmosphere, still rich in carbon dioxide and only beginning to acquire free oxygen in the places where the first cyanobacteria have begun to work. The air is warm. The wind is steady and fast, because the Earth's rapid rotation is whipping the atmosphere into constant motion. A gull, if there had been gulls, would have had to struggle against the gales. But there are no gulls. There are only microbes, sliding in their transparent films across the wet black rocks. And then, at the edge of vision, something changes. The sea, which has been a broad, shimmering plain to the horizon, begins to gather itself, not like a wave, not like a swell, like a continent of water rising up, moving toward the shore, carried on the invisible pull of the moon overhead. The water does not crash yet, it merely surges, it lifts, it climbs. From the coast, at this moment, you would hear a sound unlike anything on modern Earth, a low, immense rumble, coming from the direction of the sea, not the sound of waves, the sound of water in its millions of tons, moving inland, under the pressure of a gravitational field that has made it do so, at this hour, every 6 to 8 hours, for over 1 billion years. The water rises, first 1 meter, then 10, then 100. It keeps rising. It has not yet met the land. Not really, because the tidal bulge is still several tens of kilometers offshore, and it is still climbing as it approaches shallower water. The shallow bottom resists the passage of so much water. The bulge slows. The energy has to go somewhere. It goes upward. The wave steepens, and then it meets the shore. The inland surge of an early Earth tide was not a single wave. It was a sustained flood, water pushing, rising, flowing across the low continental margins at running speed, for hours, 1 kilometer inland, 10 kilometers, 100. The young continents were drowned, in part, with every tide. Vast regions of what would one day be land spent 4 hours under shallow water, and then 4 hours above it, every single Earth day, for longer than modern memory can hold. There is a particular image that scientists have proposed for this era. The concept is called the hemispheric tide. The idea is that because the moon was so close and the day so short, the tidal bulge, raised on the side of the Earth facing the moon, was a very large and very fast-moving thing. It moved around the planet not in a long, sinuous wave pattern like modern tides, but in a great rotating dome of water, sweeping over a quarter of the planet at a time. You did not have 2 high tides a day on early Earth. You had one enormous, rotating lump of water that chased the moon across the sky 4 times a day. When it came for hours, and when it left fast. The ebb of an early Earth tide was as violent as its rise. As the moon passed overhead and the bulge moved on to the other side of the planet, the water retreated, draining off the continents, pouring back out to sea in great, rushing currents, kilometers wide, tearing new channels through the soft basalt and sediment of the margins. These outflows carried sand, silt, organic slurry, microbial mats, and volcanic dust out into the open ocean, where they settled into the deep. Much of what we know about the early Earth comes from layers of sediment that were laid down by these tides. They are written, like pages, in rocks that are now exposed in Western Australia, in Greenland, in South Africa, in a few other patient corners of our planet where the oldest surviving crust has not yet been crumpled or melted away. Geologists call some of these layers tidal rhythmites. They are thin couplets of coarse and fine material, laid down in pairs, the coarse layer deposited during the strong incoming tide, the fine layer settling out during the quieter brief slack before the next tide arrived. By counting these couplets, and by measuring their relative thicknesses, scientists can actually read, almost literally, the length of a day at the time the rocks were laid down, the number of couplets per month, the number of months per year, the gentle modulation of spring tides and neap tides when the sun and moon conspired to increase or reduce the pull. It is a form of timekeeping so old that no clock ever made by human hands could hope to match its patient accuracy. These rocks tell us that 600 million years ago, near the end of the Precambrian, the day was already 21 hours. They tell us that 900 million years ago, it was closer to 18 hours. They tell us that further back, in the Archean, it was closer to 12 hours, then 10, then 8, then 6. They tell us, in the silent mineral language of layered sediment, that the Earth has been slowing for as long as there have been shores to remember. The story of the tides is, in a sense, the story of the moon's slow departure. Every tidal layer, in every ancient rock, is a page in a long record of the moon drifting farther away each year than the year before. The tidal bulge that once rolled over 1,000 kilometers of flooded continent now lifts a Pacific beach by a meter. The ocean that once heaved and roared in a rhythm 6 hours long now rises quietly, twice a day, in a pattern we barely notice. Something was lost. Something quiet, but immense, was lost. A world of tidal continents, where the water moved inland for half a day and then retreated. A world where life could not cling to dry rock for long, because the rock would not stay dry. A world where every shoreline was a temporary place, a line that kept moving, and where the boundary between sea and land was not a boundary at all, but a kind of perpetual conversation. Life grew up in that conversation. Life came of age on shores that were never permanent. Life learned, in its simplest and oldest cells, to endure cycles of wetness and dryness, of warmth and cooling, of concentration and dilution. And when the tides at last slowed, when the continents finally rose and stabilized, when the coastlines stopped moving by hundreds of kilometers at a time, life carried those old rhythms inland. It built tide pools in its own cells. It built daily rhythms and tidal rhythms into its very biochemistry. Inside you, right now, there are proteins that pulse on a rhythm that was first set in the tidal margins of the Archean Sea. There are genes that activate and deactivate on a daily clock, whose ancestors counted out their cycles beneath a moon that hung much closer than our own. Your body is, in a real and measurable sense, tuned to the earth of long ago, even as it lives in the earth of now. That is one of the quiet truths of deep time. Things do not disappear as cleanly as we think. The moon has drifted away, but the imprint of its closeness is still written in us. The tides have slowed, but the imprint of their fury is still written in the rocks. The day has lengthened, but the imprint of its shortness is still written in every cell that divides tonight, in every leaf that opens at dawn, in every bird that sings on a timetable older than the 24-hour day. The world we live in is a slow descendant of a world we have never seen, and every tide that still comes in, every low, quiet surge onto a quiet, modern shore, is a memory, a pale echo, a domesticated reminder of a sea that used to drown continents 4 times a day for 1 billion years. Tonight, if you listen carefully, you can almost hear it, not the modern ocean washing on its familiar beaches, but the older ocean beneath it, the fast, fierce, tidal ocean of a planet that used to spin in 6 hours, the ocean that built life, that tore down and rebuilt continents, that carried the chemistry of a young world on its back for longer than any living memory can span. The sound of the early Earth was the sound of water in motion. The sound of our world, now, is the slowly fading echo of that same motion. The moon is still pulling. The Earth is still spinning. The tides are still turning, even if they are quieter than they used to be. Nothing is ever truly at rest. By the rise and fall of shallow seas, by the very shape of the ocean, the breaking of the earth is, in every sense, a planetary process. Everything that makes our world what it is contributes, in one way or another, to the slow rhythm of its rotation. This is a quiet but enormous idea. The length of your day is not just a consequence of gravity between 2 bodies. It is a consequence of geology, of tectonics, of the specific arrangement of land and sea on the surface of your particular planet at this particular moment in its history. The 24-hour day is not a cosmic constant. It is a local accident. It is the current reading on a very slow, very intricate mechanical clock, whose hands are dragged at different speeds depending on where the ocean happens to be. 600 million years ago, during the late Precambrian, the day was 21 hours, 80 hours shorter than now. That is 20 minutes shorter than the current day. In a year, that difference matters. In 1 billion years, it is enormous. 400 million years ago, in the Devonian period, when fish were first beginning to crawl onto land, the day was about 22 hours. The year contained around 400 of those shorter days. We know this from corals. Beautiful, delicate, long-dead corals preserved in the fossil record. Corals lay down fine daily growth layers as they live, and coarser seasonal bands as the year turns. By counting the daily layers between 2 seasonal bands, you can count how many days the coral experienced between one summer and the next. The corals of the Devonian, preserved as stone in places like Michigan, recorded 400 mornings per year. Our year today contains only 365. The Earth did not speed up its orbit around the Sun. The year, in terms of its total length in seconds, is almost exactly the same as it was 400 million years ago. What changed is the day. The day is lengthened. It used to fit into the year 400 times. Now it fits only 365. Every one of those lost days is payment for the moon's retreat. Every one of those lost days is written into the slow, patient work of the tides. Every one of those lost days is a quiet geological transaction, a little bit of the Earth's rotation given up, forever, in exchange for a moon that now hangs a few tens of thousands of kilometers farther out in space than it did when those corals were young. If you had lived on the Earth 400 million years ago, your life would have been different in ways that have nothing to do with the absence of cities or the presence of primitive fish. Your day would have been shorter. You would have had less time between sunrise and sunset. You would have rested more often, relatively, because the short night would have felt more intrusive. Your internal clock would have been set to a faster beat. You would not have lived more years, because your year was the same length, in minutes and seconds, as ours. But you would have experienced more sunrises in a single year than you do now. You would have watched the sun more often. You would have felt the rhythm of light and dark arriving faster. And the moon, in your night sky, would have been a little larger, not hugely, not like the moon of the Hadean, but perceptibly larger. A touch heavier in the sky, a touch closer to the shore. The slow breaking of the world has changed the very experience of being alive on its surface, not dramatically for any individual generation, but profoundly across eras. Sometimes, when I think about this, I feel the quiet smallness of a single human lifetime. We live, at most, 100 years. Our grandparents lived through days that were, to any instrument we could build, exactly as long as ours. Our great-great-grandchildren, if they survive, will live through days that are, to any instrument we could build, exactly as long as ours. The earth is slowing, but so slowly, that for all of recorded history the change is simply invisible. All the wars, all the civilizations, all the loves and losses of human time have unfolded in a sliver of rotational history during which the day has not lengthened by even a single second. And yet, the process is inexorable. Across 10 million years, across 100 million, across a billion, the difference adds up to something that transforms the entire character of the planet. 6 hours, 9 hours, 12, 18, 21, 24, and onward, into futures that we will never see. The Earth's clock is ticking down, in a sense, or perhaps ticking up. Each revolution, each day, just a tiny fraction slower than the one before. Tonight, as you drift towards sleep, the Earth is turning, and it is turning, if we could measure it precisely enough, just slightly more slowly than it was yesterday. Not enough for you to notice. Not enough for any clock to detect in a single human life. But slowing, always slowing. The moon is doing its quiet work. The tides are paying their quiet price. And the day, which was once as short as an afternoon, is still stretching patiently towards something longer. For most of the story of life on Earth, the sky above our planet has been moving differently than it does now. Faster, more urgently, more restlessly, the sun climbing more quickly from horizon to horizon, the stars wheeling overhead on an accelerated track, the moon, still larger than the moon of today, crossing its arc of sky in fewer hours than we are used to. For a long time, life had to work in this rhythm. Life had to evolve under a fast sky. We often picture the great transitions of biology as happening on a modern Earth. We imagine the first fish crawling onto land, the first amphibians gulping air, the first reptiles laying eggs on dry stone, and we imagine all of it against the backdrop of a day that looks like our own. A 24-hour day, a small, distant moon, a calm, ordinary sky. That picture is wrong. The first fish to drag itself onto a muddy shore did not live under our sky. It lived under a sky whose sun rose and set in a little over 21 hours. The first amphibian that took a breath of air lived through nights shorter than our own, and through mornings that came faster than any alarm we have ever heard. The first reptile to nest on an inland plain lived on a planet whose tides were stronger, whose moon was larger, whose night sky held a different, closer companion. This is one of the subtle truths of deep time that tends to slip past us. The calendar of Earth has changed. Every creature that ever lived, ever ate, ever slept, ever bred, did so on a planet whose clock was running at a different speed than the clock on our wrist. Their biology was shaped by their own local time, and we have inherited the ghosts of that local time, faintly, in the biology we carry forward. Let us travel, in our imagination, to a particular moment. Let us stand on a shore of a shallow inland sea in the Devonian, about 380 million years ago. The day here is about 22 hours long. The year contains roughly 400 of those days. The moon is only slightly closer than the modern moon, but noticeable. A little larger, a little brighter. The tides are stronger than our tides, though nothing like the tides of the Hadean. They rise and fall 6 times in every 22-hour rotation of the planet. The water is warm. The continents of the world, in the Devonian, sit mostly in the southern hemisphere. Europe and North America are a single landmass, fused along a new mountain range, straddling the equator. Much of what we would call modern Asia is still submerged. The southern supercontinent of Gondwana drapes across the South Pole. The world is greener than it used to be, because, for the first time in the story of our planet, there are forests. Forests are new. The Devonian is sometimes called the age of fishes, but it is also the age of the first trees. These early trees do not look quite like modern trees. Some of them are lycopsids, giant relatives of modern club mosses, with trunks made of complicated vascular tissue and tops frilled with thin, narrow leaves. Others are progymnosperms, ancestral to both ferns and seed plants, growing to 30 meters tall, their crowns a dense crosshatch of needle-thin fronds. The floor beneath them is wet, spongy, covered with mats of liverworts and the small, low ancestors of mosses. The air is rich with oxygen. It is also thick with the scent of sap, of decay, of the first forest smells on Earth. A fish, lying in a puddle at the edge of the water, breathes through primitive lungs as well as gills. Its name, if we were going to give it one, might be something like Tiktaalik. It has fins with bony supports inside them, fingers, in their earliest form, folded beneath the skin. Its eyes are on the top of its head, like a crocodile's. It can push itself up on its fins, out of the water, to survey the land around it. It has been doing this for generations. The sky above our ancient fish is a fast sky. The sun is moving, visibly, across the green canopy. The shadows are shortening, hour by hour. By our modern reckoning, we would call it late morning, but late morning in the Devonian comes quickly. The sun has been up for only a few of our modern hours, and already it is approaching its peak. The shadows are already beginning to gather on the other side of the trees. In another 2 of our hours, the sun will be setting. In another 2 after that, the moon will be rising. For our fish, this fast sky is not remarkable. It is the sky it has always known. It is the sky its ancestors knew. The rhythm of light and dark, fast as it is simply the rhythm of being alive. The fish's cells divide on a cycle tuned to it. Its feeding is tuned to it. Its breeding, its migration, its sleep, all are calibrated to a day that fits a little more snugly into the turning of the stars. And this is true of every creature in the Devonian. The trilobites, still abundant in the warm, shallow seas, sense the rising tide and burrow when it recedes, on a rhythm matched to the 22-hour day. The corals, laying down their thin daily layers of calcium carbonate, record, in stone, 1 new band each 22 hours. The early sharks, the armored placoderms, the first ammonites, all live by a clock faster than ours. They do not notice. They cannot notice. The clock is the clock, but the clock is changing. Over the tens of millions of years that follow the Devonian, the moon will drift a little farther. The day will lengthen by a few more minutes. And the life that has adapted to a 22-hour rhythm will find, generation by imperceptible generation, that its rhythm is being stretched. No creature notices this in its own lifetime. The changes are far too slow. A trilobite born in the early Devonian and a trilobite born 100 million years later in the Carboniferous are both experiencing, subjectively, a normal day. But the day, for the later trilobite, is a little longer. The tides are a little slower. The moon is a little smaller in the sky. Over time, This lengthening has biological consequences. The cycle of cell division in photosynthetic algae, tuned for millennia to a shorter day, must slowly adjust to a longer one. The feeding rhythms of tide pool organisms must slowly accommodate a longer interval between incoming waters. The reproductive cycles of corals, spawning in synchrony with the lunar month, must follow the moon's slow retreat. None of these adjustments happen in a single generation. They happen across millions. They happen because individuals who, by chance, are slightly better adapted to a slightly longer day pass on their genes a little more successfully than individuals who are not. The adjustment is, like everything in evolution, slow and patient and almost invisible. But it is real, and it is recorded. There is a phrase in biology that I find quietly beautiful. The molecular clock. The idea that the chemistry of life itself keeps time, and that by measuring the subtle changes in the sequences of certain genes we can read, in a rough way, when different lineages of organisms shared a common ancestor. The molecular clock is not a single clock, but a collection of chemical rhythms, and some of its rhythms, we believe, are tuned to the length of the day and the length of the lunar month. Circadian rhythms, the internal daily clocks of nearly every organism we know, almost certainly arose early in the history of life. They are too universal to be a late invention. They are found in bacteria, in algae, in fungi, in plants, in animals. They work, at the molecular level, by the rhythmic accumulation and degradation of certain proteins, which activate and deactivate certain genes, in a cycle that approximates the length of a day. In most organisms today, this cycle approximates 24 hours, give or take. The human circadian rhythm, in the absence of outside cues, tends to run a little long, closer to 24.5 hours. In most people, other organisms run slightly short. Flies tend toward 23.5. Plants often run close to 24, but none of them are precisely 24 hours. Why? One possibility, proposed in some evolutionary models, is that the circadian clock originally arose in response to a day that was shorter than 24 hours, perhaps much shorter, perhaps 18 hours, perhaps 15. And as the Earth's rotation has slowed, the molecular clocks of life have been stretched slowly, through natural selection, to match the gradually lengthening day. But they have not been stretched perfectly. They have been stretched only enough to be reset, every morning, by the rising of the sun. The small mismatch, the half hour here, the quarter hour there, may be a faint chemical echo of a faster day, preserved inside the cells of nearly every living thing. If this is true, then your circadian rhythm, the one that decides when you feel sleepy tonight, and when you wake tomorrow, and when your body releases its slow tides of hormones, is, in some small way, remembering a planet you never knew. A planet with a day slightly shorter than the one you now experience. A planet whose rhythms still live inside you. You are, in a very literal sense, carrying the Devonian with you. Let us imagine one more scene from this fast sky era. Let us move forward a little, into the late Paleozoic, the Carboniferous, 320 million years ago. The day is now about 22.5 hours. The year contains around 385 of these days. The forests have grown into something astonishing. Giant lycopsid trees over 30 meters tall. Vast wetlands where the trees die and fall and pile up and become, in time, the coal that we will one day burn to run our cities. The air is thicker with oxygen than it has ever been. Perhaps 35%, much higher than our own 21. In this oxygen-rich air, certain animals grow to sizes that cannot be sustained under modern conditions. Dragonfly-like insects with wingspans of 70 centimeters glide between the trunks of the lycopsid trees. Millipedes 2 meters long crawl across the damp forest floor. Scorpions the size of small dogs hunt by moonlight. The very possibility of such creatures depends on an atmosphere engineered by the first forests, which are themselves depending on conditions, including climate and tide, set by a planet whose rotation is faster than ours. The Carboniferous night, lit by a moon still perceptibly larger than our own, is full of sounds: the cheer of giant insects, the hiss of early reptiles, the constant slow drip of water from the canopies of trees that receive, every few hours, the rhythmic pulse of fast-moving weather driven by a world that spins in 22 hours. This is not our night. This is not our forest. This is not our sky. And yet, in a way that connects us across 300 million years, this is the world that gave us our coal, our oil, our atmosphere, our evolutionary possibility. The Carboniferous sky, fast as it was, shaped the climate. The climate shaped the forests. The forests shaped the atmosphere. The atmosphere shaped the animals. And the animals, in time, gave rise, along unlikely and meandering paths, to us. Everything you breathe, everything you burn, everything your civilization runs on, traces back to a Carboniferous forest that grew under a fast sky and a close moon. Tonight, somewhere in the world, a geologist is holding a piece of coal. If she looks at it carefully, she can see the grain of its ancient plant material, preserved in dark layers. She cannot, from a piece of coal alone, read the length of the day in which it grew. But in the deeper rocks around her, in the layers of tidal sediment and coral growth and banded iron, the length of that day is still written: 22.5 hours. 385 days per year. A moon a little closer. A sky a little faster. The fast sky is gone. The forest beneath it is gone. The dragonflies are gone. The moon has drifted. But the record is not gone. It is written in the stone. It is written in the coal. It is written, subtly, in our own bodies, in the half-hour slouch of our internal clocks, in the slight quickness of our circadian pulse, in the way we settle into sleep tonight on a planet whose day is, by one measure, a little longer than we might instinctively expect. We are creatures of a fast sky, slowed down. The next time you watch a film about dinosaurs, notice the sky. The filmmakers, whether they know it or not, almost always get the sky wrong. They show a Cretaceous morning with the sun rising at a familiar pace, climbing at a familiar rate, traveling across the sky in the same arc we know. The palm fronds sway in a familiar breeze. The moon, if the moon appears, hangs at a familiar size. But the sky of the dinosaurs was not our sky. It was still, by our measure, a fast sky. Slower than the Paleozoic, slower than the Hadean, but still not quite ours. During the long reign of the dinosaurs, which stretched from about 230 million years ago in the Triassic to about 66 million years ago at the close of the Cretaceous, the length of an Earth day evolved from roughly 23 hours to about 23.5 hours, close to our own. Close enough that a time-traveling human might not notice, at first, in the middle of a busy afternoon, but not our own, not quite. A day shorter, a night shorter. An entire rhythm slightly compressed, by modern standards, even in the time of Tyrannosaurus rex. This may sound like a small thing, half an hour here, a few minutes there, and on a single day, it is small. But over the course of a year, it adds up to almost a week of extra sunrises. Over the lifetime of an individual dinosaur, which might have been 30 or 40 or, for the biggest sauropods, even 100 years, it would add up to thousands of extra mornings, thousands of extra evenings, thousands of extra turns of the sky. The dinosaurs lived in a world with more days per year than we have. Their calendars, if they had kept any, would have been crowded. More sunrises, more sunsets, more rhythms of warmth and cool, more openings and closings of flowers, more feeding cycles, more hunting cycles, more migration cycles. Their biology, like ours, was tuned to a daily rhythm. But their daily rhythm was a little faster than ours. and so their year contained a little more of everything. Stand, for a moment, on the floodplain of a river in what will one day be Montana. It is late in the Cretaceous, perhaps 70 million years ago. The day is 23 hours long. The year contains 370 days. The moon, just past full, hangs in the late evening sky, a touch larger than our own, a few tens of thousands of kilometers closer than the distance it will eventually reach by our own time. The tide of the inland sea, some 100 kilometers to the east, pulls a little stronger than a modern Atlantic tide. The night is warm and humid. The air is full of smells that no human nose has ever smelled. Cycads, conifers, the first flowering trees. Around you, the shapes of giants move through the dim blue light. A hadrosaur family, perhaps 20 individuals, is crossing the floodplain, their footsteps thudding softly into the wet mud. They are duck-billed, grazing animals, peaceful if not disturbed, built on the scale of modern elephants and then larger. Their songs, low rumbles and trumpet calls, rise into the air as they communicate across the herd. Somewhere in the distance, a tyrannosaur is watching, waiting, its own internal clock tuned to the shorter night. The dinosaurs have been living on this faster world for over 160 million years by the time of this evening. They've evolved from small, lightly built bipedal runners in the Triassic into a bewildering variety of forms. Herbivores the size of houses, predators with jaws that could crush iron, small, swift raptors, armored, tank-like creatures, gliding near birds. They dominate the terrestrial world. They have done so on a planet whose day has lengthened from about 23 hours at the start of their reign to 23 and a half at the end. A small change, spread across an almost unimaginable stretch of time. Their biology is adapted to it. Their behavior is adapted to it. Their patience, if that word can apply to creatures with brains so unlike our own, is adapted to it. They do not know that the earth is slowing. They do not know that the moon is drifting. They do not know that the day, across their long reign, is lengthening by minutes per million years. They only know their own time. They only know their own sky. They only know their own tide. There is something almost comforting in this thought. The dinosaurs lived inside a planet that was changing without them knowing. And the same is true of us. We live inside a planet that is changing without us knowing. Not all the changes are the slow rotational change of the day. Some are faster. Some are the changes we ourselves are making. But many of them are slow. Continents drifting, oceans rising, the day lengthening, the moon retreating. All of these processes are underway, right now. And none of them are perceptible to us in our daily lives. The dinosaurs did not notice the moon moving away. We do not notice the day lengthening. We live in our slice of time, as they lived in theirs. The Cretaceous night is short. By midnight, the stars that were rising at dusk are already nearing the western horizon. By what we would call 3 in the morning, the eastern sky is already beginning to lighten. The dinosaurs that sleep, and we think many of them did sleep in bursts, in cycles shorter than ours. Their brains flushed and rested in shorter doses. Their metabolism, in some of the large herbivores, kept them partially awake and feeding even through their shortened nights. The fastest metabolisms, in the smaller raptors, probably required them to rest in brief intervals during the long-lit portions of their crowded days. The sky wheels, the moon sinks, the tide pulls, the forests breathe. The dinosaurs move through a world set to a clock that is almost, but not quite, like ours. And then, on one particular spring morning in this era, something enters the Earth's sky that will end all of it. The Chicxulub impactor, the asteroid the size of a mountain, the 10-kilometer sphere of rock and metal that has been falling toward the Earth for a very long time and is now only a few hours away. The dinosaurs, on this particular morning, still do not know. The moon, hanging in its position a little closer than our own, has never seen anything like what is coming. The asteroid will strike the shallow sea of the Yucatan. The world will change. The dinosaurs, accepting the lineage that will become our birds, will vanish. And the Earth, in the aftermath, will continue its slow rotation, its tides undiminished, its days still lengthening, its moon still drifting, as if nothing had happened. Because, to the rotation of the Earth, nothing had. The impact, for all its horror, was simply another event. The planet kept turning, the moon kept receding, the day kept lengthening. 66 million more years would pass. The day would lengthen from 23.5 hours to 24. The moon would drift outward another 2,000 kilometers. Entire new lineages of mammals would rise and fall. Grasslands would spread. Primates would evolve. And finally, at the very end of this long, slow, almost imperceptible adjustment of the planet's clock, a particular species of primate would invent the measurement of time precise enough to perceive that the day was still changing. That is us. That is our place in the story. We are the species that figured out how long the day was, and that it had not always been that long, and that it would not always be that long in the future. We are the species that can read the stone pages of the tidal rhythmites and count the growth lines of ancient corals and calculate, from the pull of the modern moon, how much further it will drift before our planet no longer has anything left to give it. We are the witnesses, late but finally here. Part 5 of 5. When the asteroid struck the Yucatan and the long reign of the dinosaurs ended, the Earth did not pause. The planet did not slow its rotation for grief. The moon did not halt its retreat to mark the moment. The tides continued to rise and fall on their fast, slightly faster than modern rhythm. The day continued to lengthen, at the rate of about 2 milliseconds per century, as it had been lengthening for billions of years before the impact, and would continue lengthening for billions of years after. But the surface of the Earth had changed. A great deal of the world's ecosystems were gone. The great forests of the Cretaceous, with their cycads and conifers and early flowering trees, had burned or been blanketed in ash. The oceans, poisoned with acid rain and starved of sunlight for months or years, had lost much of their biomass. The creatures that survived were the small, the burrowing, the amphibious, and the resilient. Some of them were mammals, some of them were birds, some of them were lizards. None of them, in those dim years after the impact, would have seemed to a visitor especially important, and yet, in the recovery that followed, something astonishing began. The age we call the Cenozoic, which stretches from the extinction 66 million years ago to the present, is the age of mammals. And it is also the age in which the length of the day finally, slowly, unfolds into the length we now know. At the start of the Cenozoic, the day was still about 23.5 hours. By 10 million years ago, it had lengthened to nearly 23 hours and 58 minutes. By 1 million years ago, it had reached something indistinguishable, for practical purposes, from 24. The last decimal places were still being quietly adjusted, but the gross value was settled. The moon, during this same stretch, retreated from about 370,000 kilometers to its modern average of 384,000, still moving, still drifting, but more slowly than it had in the Hadean. The tidal friction, which had once transferred enormous energy between planet and moon, had dwindled to the gentle, constant break we know today. And the mammals, in the rhythm of this slowing world, began the long experiment of their evolution. It is worth pausing for a moment to appreciate how lucky this timing was. If the Cenozoic had begun with a day of 15 hours rather than 23.5, the entire course of mammalian evolution might have been different. The length of our day matters more to us than we usually realize. Our sleep cycles, our digestive rhythms, our body temperature regulation, our hormonal tides, all of these are tuned to the 24-hour rhythm that we have inherited from a planet that happened during our evolution, to be rotating at roughly this rate. If our primate ancestors had evolved on a planet whose day was significantly shorter, our biology would have been different. Our brains might have developed under different regimens of sleep. Our bodies might have prioritized different kinds of rest. Our social behaviors, which are shaped in part by the rhythm of day and night, might have unfolded differently. We are the children, not just of a species, but of a particular hour of our planet's history. Within the Cenozoic, a particular chapter opens that matters for our story. About 5.5 million years ago, in the late Miocene, the continent of Africa shifted its climate. The slow dance of tectonic plates pushed portions of East Africa upward, creating the Great Rift that still divides the continent today. Mountains rose, weather changed. The dense tropical forests that had covered much of the region thinned and gave way, in places, to grassland. The canopy that had sheltered countless generations of tree-dwelling primates thinned. Light fell, for the first time in that region, onto the ground. Some of the primates left the trees, or were pushed from them. They learned to walk upright, at first clumsily, then more confidently. They developed stronger legs. They developed the physiology that would, eventually, allow them to run long distances across open country. They lost their fur on their chests and backs to radiate the heat generated by their daytime activity. They began, for the first time in the history of primates, to be daylight animals in a serious, sustained way. Their day was 23 hours and 56 minutes, almost ours. They were waking in mornings that would have felt familiar if they had ever visited our time. They were sleeping in nights that were, by our measure, a few minutes shorter, but for all practical purposes, the same. The moon hung in their sky at very nearly its modern distance. The tides at the Red Sea coasts, where they may have sometimes foraged, rose and fell with almost exactly the rhythm they do today. They were the ancestors of us, primates in the final stages of becoming something new. And they did their becoming on a planet whose clock had finally slowed to within a whisker of its current rate. We carry this inheritance in our bones and in our biology. But we also carry it in something subtler, and perhaps more important. We carry it in our expectation of what a day is. When we imagine time, we imagine 24 hours. We imagine morning, afternoon, evening, night. We imagine the sun climbing and falling in a particular arc, the moon appearing and disappearing on a schedule that fits, with soft margins, into our weekly calendars. We imagine all of this as though it were natural, as though it were inscribed into the fabric of the universe, as though any rational being on any planet would experience time the way we do. It is not so. On Mars, a day lasts 24 hours and 39 minutes, close to ours, but not the same. On Jupiter, a day lasts about 10 hours. On Saturn, about 11. On Venus, a single day lasts longer than the Venusian year, the planet turning so slowly that the sun rises only twice in the course of a full orbit. On Mercury, a single day-night cycle spans nearly 176 Earth days. Time, on other worlds, is a different animal entirely. The 24-hour rhythm is not a property of the universe. It is a property of our particular planet, at a particular stage in its history, with a particular moon at a particular distance. It was 6 hours once. It will not remain 24 forever. But before we travel forward, we should pause, for a moment, on the strangeness of our current moment. We are alive in a time when the length of a day feels completely stable. Over the course of an entire human civilization, from the first cities to the present, the day has lengthened by roughly 15 milliseconds. Not seconds, milliseconds. A change so small that no unaided human instrument could have detected it at any point in our history before the 20th century. And yet, that change has happened. It is happening now. Every day on Earth is, at the measurable level, longer than the day before. The sun, tomorrow, will take a little longer to climb the sky than it did today. You will not feel it. No one has ever felt it. The lengthening is real. and it is patient, and it is hidden from every human sense. This is one of the quiet strangenesses of deep time. Some of the most important processes on our planet are invisible to us on any time scale we can personally experience. The movement of the continents, the drift of the moon, the lengthening of the day, the cooling of the Earth's core, the aging of the sun, these are the deep rhythms of our world. They are all in motion. They have always been in motion, and we, who live in our flash of 80 or 90 years, have the strange privilege and strange limitation of being able to measure them, but never to feel them. Tonight, as you lie quietly in the dark, the Earth is turning. It is turning a fraction more slowly than it turned a century ago. A fraction more slowly than it turned 1,000 years ago. Much more slowly than it turned 1,000,000,000 years ago. And the moon, unseen outside your window or behind the clouds, is in its own slow escape, drifting, retreating, moving away by about a centimeter per year, though the whole of its patient journey. This is the sound of the world growing up. Not a sound, really. A process, a settling, a calming, a long, slow breaking of the wheel that carried us through our violent infancy into our current quiet middle age. We live inside this quiet. We live inside this slowly lengthening day. We live inside this outward drift of the moon, and we are, so far as we know, the only part of the planet that has ever thought about any of it. There is a particular kind of clock that humans have built in the last century that is capable of detecting the lengthening of the day. It is called an atomic clock. It measures time by counting the vibrations of a cesium atom, which oscillates at a fixed, unvarying frequency dictated by the laws of quantum mechanics. Atomic clocks do not care about the Earth. They do not care about the moon. They do not care about the tide. They simply count, with staggering precision, the vibrations of a single kind of atom, and they convert that count into a definition of the second. Using atomic clocks, and comparing their measure of the second to the actual rotational rate of the Earth, scientists are able to measure, in real time, exactly how fast our planet is spinning. And what they have found confirms, quietly and precisely, what the ancient rocks have been telling us for decades. The Earth is slowing. At the current rate, the day is lengthening by about 2 milliseconds per century. That is 0.002 of a second, added every 100 years. An extraordinarily small amount, but a real amount. An amount that, over the course of 1,000 years, equals 0.02 of a second. Over the course of 1,000,000 years, equals 20 seconds. Over the course of 1,000,000,000 years, equals more than 5 hours. 5 hours. That is the difference between the day we now live in and the day that primitive life first evolved to live in. That is the difference between our comfortable 24-hour rhythm and the fast, pulsing 18-hour rhythm of the early Archean Ocean. 5 hours, laid down across 1,000,000,000 years at a rate of 2 milliseconds per century. And yet, the rate is not even constant. There are small fluctuations. The ocean currents, the atmosphere, the core of the Earth itself, the melting of glaciers, all contribute to tiny, measurable variations in the rotation. When a huge earthquake shifts mass closer to the axis of the Earth, the day shortens, very slightly. When a vast volume of water shifts from one hemisphere to another, the rotation changes. Even the changing distribution of ice on the continents, melting from Greenland and Antarctica, affects the spin. The Earth is, in its rotation, a sensitive instrument. It registers every major rearrangement of its own substance. The moon is the main driver of the long-term lengthening, pulling the brakes steadily through its tidal friction. But the day-to-day fluctuations are a chorus of smaller voices: the winds of the atmosphere, the currents of the sea, the slow creep of the core beneath our feet. This is why, about every year or two, the world's official timekeepers announce a leap second. They add 1 extra second to the official calendar to keep atomic time aligned with the Earth's rotation. When the Earth slows just enough that the difference between atomic seconds and actual sunrise has accumulated to a full second, the keepers of time quietly insert a 61st second into the minute before midnight, somewhere in the year, and the world's clocks quietly absorb it. We live, in other words, on a planet whose rotational pace is so uncertain, so slightly variable, that our most precise timekeeping system has to be manually corrected every so often to keep pace with the actual behavior of the sky. The Earth keeps its own time, and we, in all our sophistication, are only just barely able to keep up. This is a small, quiet reminder that we are guests on a rotating world. We are not its owners. We are not in charge of its rhythm. We are simply here, riding it, for the few decades we get to ride it, tuning our clocks, when we must, to the great and imperfect motion of our host. As the day continues to lengthen, some interesting things will happen. Across the next 100 million years, the day will stretch to roughly 24 hours and 40 minutes. A creature living then, if any of our descendants or any intelligent successor species is present, will experience a day noticeably longer than our own. The difference is small, but it is real. And across the following billion years, the day will stretch further. It will pass 30 hours, then much later, 40. It will do so with the same unbearable patience that carried it from 6 hours to 24, milliseconds at a time, minutes over millions of years, hours over hundreds of millions. What would this future Earth look like? It would look, in many ways, like ours. The continents will be arranged differently, because tectonics does not pause. The sun will be brighter, because stars grow more luminous as they age. The climate will be warmer. Life, if it persists, will have continued to evolve into forms we cannot guess. But the most important change, for our story, will be in the moon. As the moon drifts further from the Earth, its apparent size in the sky will shrink. We are already, right now, near the end of a beautiful coincidence. The sun and the moon, seen from Earth, appear at almost exactly the same size in our sky. This is why we have such dramatic total solar eclipses. The moon's disk fits, almost perfectly, over the sun's disk, and for a few miraculous minutes, day becomes night. The stars appear. The corona of the sun flares against the black of space. This coincidence is accidental. The moon is much smaller than the sun, but much closer. The ratio of sizes and distances just happens to work out to almost exactly 1-to-1. If the moon were any further away or any closer, total solar eclipses would not look the way they look, and the moon is moving away. In 150 million years, the moon will be too distant to completely cover the sun. Our descendants, if we have any, will no longer witness the strange and sacred darkness of a total eclipse. They will see, at best, an annular eclipse, where a ring of sunlight still burns around the moon's receding disk. The black corona-ringed sun, which our ancestors took as an omen and our generations have photographed as a miracle, will be gone, replaced by something less dramatic, something paler. The moon, in the deeper future, will be a smaller and smaller point in the night sky, still visible, still bright, but diminished. The great looming silver companion of the Hadean will have finished its long journey outward, and the Earth, below, will turn a little slower, a little slower, a little slower. Eventually, we reach the limits of our own projections. The slowing of the Earth does not continue forever. There is a point, far in the future, at which the Earth's rotation will match the moon's orbit. Both bodies will rotate and revolve at the same rate. The same face of the Earth will always face the moon. The same face of the moon will always face the Earth. The system will be locked, tidally locked. Just as, already, the moon's same face always points toward our planet, the Earth's same face will always point back. This is the end point of tidal evolution, a system where both bodies turn in step, where the tides no longer transfer energy, where the day and the lunar month become the same length. The calculations for when this would happen, if nothing else interfered, suggest a day of about 47 hours, locked to a lunar month of the same length. The moon would sit in one particular portion of the sky, visible only to one hemisphere of the Earth. The other hemisphere would never see it again. But this final state will never arrive. There is not enough time. Long before the Earth and the moon reach tidal lock, the sun will have entered the later stages of its stellar evolution. In about 1 billion years, the sun will have grown roughly 10% brighter, bright enough that the Earth's oceans will begin to evaporate. Over the following 1 or 2 billion years, the surface of our planet will become uninhabitable. The atmosphere will thicken with water vapor, then escape into space. The ocean will shrink. The continents will become dry. Life, if it persists, will retreat into increasingly narrow niches. In about 5 billion years, the sun will expand into a red giant. It will engulf Mercury, and then Venus. It will likely swell to the orbit of the Earth, or beyond. Whether our planet is swallowed entirely or escapes in some form is still debated. But whatever remains of the Earth will not be anything we would recognize. Oceans gone, atmosphere gone, crust likely melted or stripped. And the moon, if any remnant survives, will be a small piece of rock circling a small piece of rock, both of them orbiting a dying star. The Earth will never reach the 47-hour day. The slowing will end, not because the physics of tidal braking stops, but because the sun intervenes. The engine runs out of fuel. The planet runs out of time. This is one of the humbling truths of deep time. The processes we study, the slow rhythms of our planet, are not going to complete themselves. We measure their course across millions and billions of years, and we plot their long asymptotes into the future. But the universe is not patient enough to see them finish. The sun has its own schedule. The planet has its own mortality. The moon has its own fate. Everything ends, in its own way, before the slow equations complete. The day, then, will not lengthen forever. It will lengthen for a while more. It will pass through 25 hours, and 26, and perhaps 30. It will do so at the patient, milliseconds per century pace it has kept for as long as we have records. It will carry all of life on Earth, or whatever descends from us, into longer days, longer nights, larger skies, and then, at some point, long before the clock runs out on 47, the sun's own growing heat will end it. We live, in other words, in the middle of a process. Not at its beginning, not at its end, just in the quiet middle stretch, between a young Earth with a 6-hour day and a dying Earth with no day at all. Tonight is one of those middle nights. There is a kind of ending that we have already touched on, but that deserves its own contemplation. The spinning of our planet, the rotation that defines our day, is not eternal. It will end, one way or another, if not by tidal lock, then by the death of the sun. If not by the death of the sun, then by some other cosmic turn we have not yet thought to include in our models. Nothing turns forever. This is worth sitting with. The day, the most familiar unit of our lives, the rhythm by which we measure everything from our heartbeats to our calendars to our long, slow slide towards sleep, is temporary. It has changed enormously already. And one day, it will stop. What would a stopped Earth look like? It depends on how the stop happens. If the Earth became tidally locked to the moon at 47 hours, the planet would still rotate, but only in pace with the moon's orbit. From a stationary observer's perspective, the Earth would still turn, but slowly. The sun would still rise and set once every 47 hours. There would still be day and night, just much longer ones. Half the world would be locked in 23 hours of continuous daylight, followed by 23 hours of continuous night. Weather patterns would be dramatically different. Life, if any remained, would have to cope with temperature swings between the long day and long night that our current ecosystems cannot imagine. But this is not likely to happen. As we have said, the sun intervenes first. If the Earth were, by some accident or impact or catastrophe, to lose its rotation entirely, the consequences would be severe in ways that are almost poetic. One side of the planet would face the sun permanently. The other side would face away. The sun side would slowly roast. The far side would slowly freeze. The atmosphere, stirred by the enormous temperature difference, would tear itself into storms of unprecedented fury until it found some new, strange equilibrium across the permanent day-night boundary. Life on such a planet might still exist, in narrow bands along the terminator, the eternal twilight line where day and night meet. Some planets around other stars may indeed be like this. Tidally locked worlds, where the only habitable places are the shores of perpetual sunset and sunrise. We may one day, if we survive, visit such worlds. But the Earth, we believe, will not reach this state. Not by tidal lock, not by gentle retreat. It will instead be overtaken by the sun, which will grow brighter, hotter, larger, until our planet is no longer recognizable. Our slow rotational slowdown will be a note in the obituary, not the cause of death. This is the quiet ending of the story of our day. It does not end with the satisfying click of a clock whose hands have finally stopped. It ends, instead, with the day still slowly lengthening, as the sun grows brighter, as the oceans boil, as the biosphere retreats and eventually vanishes, as the planet becomes sterile, and finally, much later, as the sun itself fails. At some point in the very far future, there will be one last day on Earth, one last dawn, if there is anyone to notice it, one last dusk, one last turning of our world beneath the old sky. And then, however it happens, the rotation will end. We will not be there to see it. Almost certainly, no one who thinks will be there to see it. The day began before any thinking creature existed, and it will likely end long after the last thinking creature is gone. But it will have been, across its span, one of the longest and strangest processes our little corner of the universe will have ever known. A process that began with a collision between two young worlds. A process that ran through the chemistry of the first oceans. A process that shaped the rhythms of life. A process that set the pace of all our biology. A process that determined, in 1,000 subtle ways, what it meant to be alive on this planet. The day. Just the day. The quiet, familiar rotation of the Earth. A thing we take so utterly for granted that we have to be reminded, deliberately, that it has a history, that it has a course, that it has, somewhere in the very far future, an end. Tonight, the day is 24 hours long. Tomorrow, it will be a few fractions of a microsecond longer. In 100 years, a few milliseconds longer. In 1 billion years, hours longer. And eventually, when the sun or some other circumstance intervenes, it will stop entirely. Every sunrise you have ever witnessed was a small, unrepeatable miracle in a history that runs from a 2-hour spin to nothing at all. Every sunset you have ever watched was a moment inside a process that we are only just barely able to perceive. Every night you have ever slept through, including this one, has been, in its quiet way, a night inside a day that will never come again. The day you are living tonight has never existed before, at exactly this length, in the 4.5 billion year history of our planet. It will never exist again. Tomorrow will be a tiny fraction longer, and the day after, longer still. Each day is a little slower than the last, each sunrise a little later. We tend to think of time as something that repeats, days, weeks, years, the same rhythm, over and over. But at the deeper level, no 2 days are the same length. No 2 days are the same rhythm. The Earth's clock is always slightly slowing. The night sky is always slightly changing. The moon is always always slightly further. We live inside a world that never comes back. This is, in one sense, a lonely thought. Each moment gone forever. Each day a one-time event. Each sunrise the only one exactly like itself that will ever occur. But in another sense, it is a tender thought. It means that every sunrise is precious. Every sunset is unrepeated. Every quiet moment, like this one, is a moment carved out of a process so slow, so vast, so patient, that it dwarfs everything we have ever done and everything we will ever do. To be alive, in a particular day, in a particular stretch of deep time, is to witness something that will not recur. The earth has had 6-hour days. The earth has had 18-hour days. The earth has had 22-hour days. The earth will, someday, have 30-hour days. And inside all of that, just now, just tonight, we have our 24 hours, our familiar rhythm, our comfortable pace. It is a gift. It is a passing gift. It is a gift we did not earn, but that we are lucky enough to inherit. We have traveled, tonight, through 4.5 billion years of deep time. We have stood, in our imagination, on the shore of a molten planet beneath a moon that filled the sky. We have watched the first oceans form, and the first tides rise, and the first life stir, under a day that lasted only 6 hours. We have walked through the Hadean, the Archean, the Proterozoic, the Paleozoic, the Mesozoic, and into our own Cenozoic. We have watched the moon retreat. We have watched the day lengthen. We have watched the rhythms of life be slowly stretched from a faster world into the slower world we now inhabit. We have seen that the tides of the early Earth drowned continents in walls of water a kilometer high. We have seen that the moon, 4 billion years ago, hung so close that it cast shadows sharp enough to read by. We have seen that life itself, in its oldest and deepest chemistry, still carries the memory of a faster day. We have seen that the dinosaurs lived under a sky that was not quite ours, and that the great forests of the Carboniferous grew beneath a sun that climbed the sky in less than 11 hours. We have seen that the day you are living tonight is not a constant, but a process. A specific moment in a slow, long, patient unfolding that began when two young worlds collided in the dark of the early solar system. And we have seen that the process is continuing, even now, even as you rest. The moon is still moving away. By the time this morning becomes tomorrow morning, the moon will be a tiny fraction further from us than it was when we began. The Earth's rotation will be a tiny fraction slower. The day you wake into will be a tiny fraction longer. No one will notice. No instrument in your house will register the difference. But the difference will be real. And the world you wake into will be, by the quiet arithmetic of deep time, a world slightly different from the world you fell asleep in. This is the deepest rhythm of our planet. Not the rhythm of the seasons, which is a human rhythm. Not the rhythm of the days, which is an inherited rhythm, but the rhythm of the rhythm itself, slowly, patiently adjusting across the billions of years, as the moon drifts, as the tides work, as the earth turns, as the sun shines. We tend to think of permanence as a virtue. We build our monuments in stone. We mark our calendars with dates that are meant to recur. We imagine the stars as fixed, the continents as stable, the day as a constant unit of measurement, and in the time scales we live with, these things are all, roughly, true. But beneath them, everything is moving. Stone weathers, continents drift, stars age, days lengthen. The universe is a great, slow river, and we are leaves on its surface, and we mistake our small drift for stillness only because the river is so large. To hold this knowledge, gently, as you drift toward sleep, is not a sadness. It is, I think, a kind of grace. It means that the moment you are inside, right now, with your breath slowing and your shoulders releasing into the cushion or pillow beneath you, is a moment unlike any other in the long history of our planet. You are alive on a night that no other night will ever match exactly. The Earth is rotating at a speed it has never rotated at before. The moon is at a distance it has never been at before. The tide, somewhere in the world, is rising at a height it will never rise at in quite the same way again. And you are here, inside all of it, hearing this story, settling into your own small share of the planet's long rhythm. The Earth does not need you to be awake. It will keep turning whether you sleep or not. The moon does not need you to watch it. It will drift in its slow departure whether you see it or not. The tides will rise. The day will lengthen. The forests will breathe. The oceans will keep their patient murmur. All of this will continue without you tonight, while you rest, while you let the long, slow rhythm of the planet carry you where it carries you. Let it carry you. Let the rotation of the Earth, so small and so immense, rock you like the slowest cradle that has ever existed. Let the retreat of the moon, so quiet and so relentless, be the hand that dims the lights inside you, one by one, until only the softest candle of awareness remains. Let the 24 hours of our current moment be the safe, familiar rhythm inside which you fall asleep. The Earth was once a glowing wound spinning in the dark. The moon was once a red disk close enough to touch the sky. The sea was once a mountain of water, crashing across a planet with no eyes to see it. All of it happened. All of it is true. And all of it led, through 4.5 billion years of patient adjustment, to this single night, to this single room, to this single breath you are taking now. You are the slow answer to a question the early Earth did not know it was asking. You are the quiet witness that the rhythms of the planet finally have, after so long being unseen. You are a passenger on a world that is still, at this very moment, turning a little more slowly than it did yesterday. Tonight, as you drift, remember, the day was once 6 hours long. The day is now 24. The day will one day be longer. And all of it, every last second, is held by the silent friction between a world and its moon. A conversation that has been carried on in the language of tides and stone for longer than any living memory can hold. Somewhere in the world, right now, it is dawn. Somewhere, the sun is climbing the sky at the same patient rate it has climbed for the last several 100 million years. Somewhere, a shore is being touched by water that has traveled, in one form or another, from the Hadean oceans to this moment. Somewhere, a creature is waking into a day a fraction longer than yesterday's, and going about its small, perfect life, unaware. We are all, every one of us, living inside a slow widening of time. Every night is slightly longer than the night before. Every dawn is slightly later.